related rates. In this session, we will solve a couple of problems which are related to related rates. Example number 1. A paper cup has a shape of a cone with a height 10 centimeters and radius 3 centimeters at the top. If water is poured into the cup at the rate 2 cubic centimeters per second, how fast is the water level rising when the water is 5 centimeters deep? We see a beautiful graph. We see the big cone, the paper cup, radius 3 on the top, the height 10. And we see the blue cone, which water actually create that cone, and radius r and height h. Height, of course, is not 5. We know that it's not exactly 5. We're looking for the rate of change at the moment when it's 5, but it's constantly rising because the water is coming in. Okay, we always start this type of exercise with the given, required information, and the relation. Given information is the rate of change, and we may easily recognize cube. Its meaning, it's actually volume. dVdt, 2 cubic centimeters per second. And of course, 10 and 3, the dimensions of the cup. But with respect to the rates, that's given, dVdt, and we're looking for how the height is changing, dH dt, the rate of change of height with respect to time. At the moment when the height is 5 centimeters, yes, the water level is 5. It's not, of course, 5, but we're looking at the rate of change at that moment. Okay, the relationship is formula of the volume of the cone, 1/3 pi r squared h. Everything is perfect except that r radius. We really have to remove that. We have to replace r with the formula which actually it's related to h. And we may notice we do have similar triangles, okay? And we will get the relation. We have a triangle, big one, 3 and 10, and we have the blue one, small one, R and H. And again, H is not 5, because that's sometimes the common mistake that we will substitute instead of H here 5. I will put blue because it's the blue. Okay, let's get any radius over height, radius over height, radius over height, radius over height. 3/10 equals to r over h. Let's cross multiply and solve for r. And let's take this formula and substitute to the relation. Okay. Before differentiation, let's avoid product because we are able to. That's the same function. Let's square 3, h and 10. That's the result. H squared times h is h cubed. And just 9 divided by 3 is 3. 3 pi over 100. Okay. Beautiful, simple relation. Okay. Let's differentiate. With each quantity, it's the function of time. dVdt, that's the rate of change of the volume with respect to time, that's constant. Now h cubed. Derivative of h cubed is 3h squared times dH dt. Now it's the moment to substitute everything. The rate of change of the volume and the height is 5. This is the moment. And 3 times 3 is 9, 9 pi, and 100 divided by 25 is 4. 4 times 2, 8, 8 divided by 9 pi centimeters per second. We will just leave this explicit form. It's definitely less than 1. It's not really fast, but yeah, that's the answer. Example number 2. Similar, it's cone, but the water is actually in different place because now the cone is not upside down. It's just sitting on the base properly. Water flows into the conical container at the rate 2, the same rate, cubic meters per second. Assume that the container has a height of 3 and the base radius of 2. Okay. How fast is the water level rising when the level is 1 meter and then when the level is 1.8. We will just repeat the calculation for 1.8. Okay, that's me. First of all, we have the entire cone. I can maybe use this a little bit too far. The height, I mean, I have to be careful. This is actually 3. Okay, I can put 3. This is radius 2. And the same I can put here. Yes, 3 and 2, the whole container. Now, let's put more labels, but let's just look what I have. In order to define the amount of the water, the volume, because we have to define this, we will basically take the whole container minus the small one on the top, the air. We have to just subtract that volume. Okay, that means this is the whole container minus the space above. Right? That means now let's label properly, and that will be our formula, our relation. Okay, but what I would like to say, okay, that means now everything depends on the space above, because since the space above will be the volume, the space above will be changing, the amount of the water will be changing. That means this is radius, which is changing, and that height, that distance, of course, the entire distance is 3, and I will just subtract h. That means if this is h, this is 3 minus h, the entire is, yeah? We know if this is 3, we subtracting h, this is 3 minus h. Oh, so messy. Okay, I mean, I can say this one is 3 minus h, and this will stay r. This will stay r, just instead of r sub s. Okay, that means now let's look at the formula. Oh, we need given and required information, because I didn't type this one. Let's make short. Given information is the rate of change of the volume of that, yes, that water, 2 cubic meters per second. Cubic meters per second. The required information is the rate of change of height of that water, h, and our graph represents. Yeah? And at the moment, when h is 1 meter, or when h is 1.8 meters. But nothing is 1, nothing is 1.8. Okay, this will be at the end. Okay, that means let's get the relationship will be actually this: volume of the water equals to 1/3 pi. And yes, I didn't type this, supposed to be r and h, but I don't want to be confused. But we know that the radius is 2 squared times h, 1/3 pi r squared times h, minus 1/3 pi, and let's say r and h, we know that is 3 minus h actually. Yeah, the h of that space, it's 3 minus h with respect to that h. Okay, everything sounds good for, oh, wait a minute, I think I can put 3. Okay, for pi, yeah, because 3 and 3 can be cancelled out, minus 1/3 pi. And now we perfectly fine to keep this, but we're not really fine to have r. Since we're looking for the HDT, we would like to relate only volume and only h. That's the only variable that we would like to see. I mean, we have to find the relation for radius with respect to h. We will use similar triangles. You may guess this. We do have similar triangles. Let's put the, actually we can see them nicely here. 3 and 2, right? And then 3 minus h over r. Okay, 3 and 2, and the space above is 3 minus h over r. Let's get the relation. 3 over 2 equals to like 3 minus h over r. And we have to solve for r. Let's do this way. 3 over 2r equals to this. And then r equals to 2/3. Because we have to divide by 3/2. Dividing by 3/2 means multiplying by the reciprocal. Okay, this is the relation that will travel here. 2/3. Oh, this is supposed to be square. 3 minus h and everything squared. Okay, because it's r squared, the area of the circle. Right? 1/3 pi r squared. That means this is the relation for r with respect to h. Okay, let's see. 4 pi minus 1/3 pi. And what we have? 2/3 will become 4 over 9. 3 minus h squared. And another 3 minus h will give us cube. Okay, I think now the relation looks quite good. We may take this relation and differentiate. I don't know if we will have enough room. Okay, we're taking this relation and we differentiating with respect to time. Derivative of the volume with respect to time, derivative of the constant is 0. Copy that constant. Oh, actually, I'm supposed to put 1/3 pi times 4 over 9, 27. Okay, that's constant. Now, 3 minus h cubed derivative. It will be 3 times 3 minus h squared times derivative of the inner function. Derivative of 3 is 0. Minus derivative of h is dh dt. Negative, of course. Okay? And now we can substitute everything. Let's start with 1. We will substitute 1. But maybe I can nicely solve it. dv dt. That negative and this negative will become positive. That means I can say 4 pi over, actually over 9, because 27, this will become 9, this is 1. And then 3 minus h dh dt. Let's solve for dh dt. Let's solve for dh dt. I can maybe repeat this. dv dt equals to 4 pi over 9. 3 minus h squared dh dt. I mean, what we will do? Oh, let's actually substitute. Let's substitute what we can substitute. The rate of change of the volume is 2. It will be easier. And we're looking for the rate of change of height at the moment when height is 1. Okay, then it will be easier. And we will solve for dh dt. What we have? Okay, let me copy one more time. 2 squared will be 4. So let's divide everything. dh dt. We will multiply by 9 and divide by 4 pi and 4. I believe that's the number. Let's check. 2 and 2, this will become, we can 8. Okay, and it's h, this like a length, the line segment, which was in meters per, I'm just checking, second, meters per second. Okay, that means this is the explicit way, but just in case, if you need the decimals, I think I did my calculation somewhere, this will be 0.03581 meters per second. Okay, so that's the rate of change of the height, 0.4 meters per second, when height is 1 meters at that moment. And we may probably guess, okay, let's do the same calculation. The rate of change of the volume with respect to time. The same formula. I want to, this one, 2, 4 pi over 9. And now we were asked to do at 1.8 meters, when the height is 1.8. This was height, and this is height. Actually, I like to see the analogy. I know you can probably think it's crazy, but when we're looking later at the notes, it's much helpful. Okay. Squared, and we're looking for the HDT. Okay, that's what we will have. We will have 2, 4 pi over 9. This will be 1.2 squared dh dt, and let's see, dh dt 9 times 2, and divide by 4 by pi and by 1.2 squared, which actually we know what it is. Then dh dt will be, we can say 9 because this is gone, and 2 times, well, we're squaring this, right? It will be 144. When we square this is 144. And when we multiply 2 times 144 will be 288 pi. Yeah, I'm just trying to do the math without the calculator. But if this is, let's just keep maybe, I did this 2 times 1.2 squared. 1.2 squared is 1. Okay, and we may guess this is 9, or the first one was 9 over 8 pi. This one is 9 over less, 2.88 pi. That's when we, like, just arithmetically, when the denominator is smaller, the whole fraction is bigger, which this results with the bigger rate of change. And I think I did. It's 0.9947. Yeah, because this is almost 3. This is a little bit more than 3. 3 times 3, 9. 9 over 9, 1. If we had to estimate, we will say 1, and this is almost 1. Of course, meters per second, meters per second. If we need the explicit form on the test, we will do this. If we need the decimals, maybe for the homework assignment, we will provide this answer. Okay, we may guess when the height, when the water level is like rising, the rate of change is faster, because let's see, it's like cone, it's getting narrow. That means the rate of change of the flow of the water is the same, but we will rise the height faster, and we prove it. It's faster because it's higher. Okay, that means this is 2 cones problem, and I will also provide other examples. Watch the videos. Enjoy the cone. Thank you.